This burst test is what's called a UBP. It's an ultimate burst pressure test. And the reason we say ultimate is because we want to bring it to failure. I'm Sean Buckley, Chief Engineer of Life and Node at Sierra Space. Life Habitat is an inflatable system which is made of a series of soft goods layers. And those soft goods layers, under pressure, are deployed to an expandable volume that you can use in space. In preparing the article, there are several things that we want to do. And in that preparation, we take a look at the exterior of the article. We make sure that all the elements are cohesively working with each other. We make sure that the area around the article is going to provide us with the data we want from the test. If we want to keep expanding and we want to keep moving to new reaches and new heights, we have to embrace technologies that we're not comfortable with. Soft goods is one of those. And soft goods for habitation is a game changer.
LIFE stands for Large Integrated Flexible Environment. It's an inflatable habitat. It's very flexible when it's not pressurized, but once it's pressurized, it is like a rock, and it's stronger than steel, 5 times stronger than steel. The idea is it launches in a packed state, and then when you get on orbit, you inflate it so you have more volume and you have more room to live, work, and function. Hi, I'm Gerard Valle, and I'm the Structures, Mechanisms, and Soft Good Lead for Sierra Space Life Habitat. We're really just testing the structural restraint layer, which is what carries the load, and it's 1/3 the size of a life habitat.
So the restraint layer is made up of a material called Vectran. Vectran is an extremely high-strength material, performs really well in this application. It gets us the best performance while maximizing the livable volume inside the habitat. My name is James Kerwin, and I'm the Program Manager for Habitats at ILC Dover. Years of research have gone into perfecting how it's woven together, how it's sewn together. What this test is demonstrating is that we can achieve a higher factor of safety requirement than even hard structures can.
There's a lot of preparation in order to get the module prepared for test. So right now we're doing a low pressurization. We'll bring it up to a low pressure. A team will go out there, they'll take a look at the system, make sure the architecture looks good, and then we'll start to ramp it up. Take a couple hours for us to get there.
So the goal is 180 PSI or larger. I'm looking forward to the day playing out. And the more margin you get, the further ahead we are. If we don't get to 180 PSI, it's a step backwards. So getting to that first gate is important, and then progressing from there.
This test is important because running models and analyses can only give you theoretical results. You need the hard data to back up the research that we've been doing.
So we have a set of high-speed cameras, and the high-speed cameras are what will capture the actual event. With the high-speed, you'll be able to see exactly where the failure initiated, because it usually starts in one location, propagates throughout the whole test article.
Yeah, let's go! Great day for the LIFE program, great day for ILC, for NASA, our partners, and Sierra Space.
You can design and analyze something, but you don't really know until you run a test. And typically you test beyond the design capability.
Oh, the clever spring. Wow, look at that.
I think we're at an inflection point where the technology is about to be kicked off and utilized, so very excited about the next steps coming up.
The seam is right up here, and the seam is typically the weakest point in the design. So for it to have not failed at the seam is very interesting. And it goes back to wanting to see the high-speed footage and finding out what ultimately caused this.
This is a highly successful test. Our expectations were to meet and exceed the 182.4 PSI, and we burst at 192, which was incredible for us. Pretty amazing.